So I was asked to give you a greeting, and so I greet you in behalf of the Prokhorov Institute, as I have been greeted just a few minutes ago. But I would like to give you a few thoughts. I won't say advice because I don't think I am wise enough to give true advice, but a few thoughts that might be useful for you as young scientists, young physicists, just early stages of your careers. Let me begin with some remarks about the importance of loving the work that you do. When I was 4 years old, my grandfather told me that when I was 4 years old, When I was 4 years old, my grandfather told me that I will succeed in life if I find a job that is like play, that I enjoy just as much as I enjoy playing. And so I did succeed in life. I found physics, and I love physics, and loving physics was central to success. I chose to work on an effort for detecting gravitational waves that for me took half a century. And to work a large fraction of my effort in one area for half a century, I'm often asked, how did you keep going? And a big part of the answer was it was so much fun that even though it was an enormous amount of work, the fact that I loved it and I enjoyed it was central to keeping going on this for 50 years. My granddaughter has decided she wants to be a physicist. And through her undergraduate studies and her first 2 years of graduate work at Carnegie Mellon University, I kept telling her, you don't love physics enough. But physics is a field that can be used as a starting point from which to go in many directions. And so you look for something else where you can use your physics preparation that you will love, and that you should do something that you love in your life. Fortunately, she got involved in the experiment called Katrin in Karlsruhe, Germany, to measure the mass of the neutrino, and she loves it. So I no longer tell her she should leave the field. But I think it is tremendously important. If you're going to spend your life, a large portion of your life, working on something, it should be something that you love. On the other hand, I learned through my career that almost anything can be interesting. Much of my effort during my career has been on the engineering side of physics, trying to design ways to control noise in gravitational wave detectors, and designing, actually, as a theorist, designing experimental apparatus that is rather similar work to what an engineer does. And I found that extremely interesting. I worked for some time on designing solid propellant rocket engines. That was very, very interesting. I've worked in geophysics at times of my career. That was fascinating. And so you can come to love many things that might surprise you. When I arrived at Caltech in 1958, that's a long time ago, I'm 78 years old. When I arrived at Caltech as a first-year student, the other students were comparing their IQs. Now, IQ is intelligence quotient, some measurement of how smart you are. My IQ is 10 points lower than any other IQ that I heard the students quote. I realized that I was dumb. But I came to understand that a big part of that was my mind works more slowly than the minds of other people, and that's still the case. And so I realized that I had to find ways to compensate, ways to take the kind of intelligence that I had and make use of it effectively. And so one thing that I would highlight that I did was I started as a student. When I learned anything really important, I would make my own description of it and my own derivation of it as a theorist, different from the derivations I got in a lecture or a class. And that way I came to understand things and master them much more deeply than most other physicists did. And so that was one of my techniques to succeed. And I am proof that it's possible to succeed when you're not as smart and not as swift, not as fast and mentally as your colleagues are. I would like to mention, of course, that different minds work differently. Fritz Zwicky, who was a friend of mine, he invented neutron stars. He predicted that they would be produced in the collapse of a normal star and would cause supernova explosions. He was the first person to conceive of the idea of dark matter and give arguments that it exists. And he was incapable of doing a serious physics calculation, although he was a theorist. You look at his papers on the theory of neutron stars, and they're largely nonsense. But he had a tremendously deep physical intuition. He was not well appreciated in his era. We look back on him now as having really understood things very deeply, somehow from his intuitive sense that he didn't understand mathematically. By contrast, another close friend of mine, Chandrasekhar, was extremely strong mathematically, but he had no physical intuition at all. A Nobel laureate for his work on the maximum masses of white dwarfs and the necessity of collapse of stars to form what we now call black holes. His great discoveries were all made by manipulating the mathematics, not knowing where he was going in a physical sort of a way, but getting the physics out of the mathematics. And it's quite amazing to me what he could do with no intuition. Amazing to me what Zwicky could do with no mathematical capability. Jakub Borisovich Zeldovich, again a close friend of mine, was somewhere very much in between. He had a tremendous ability intuitively to identify the central pieces of physics in a complicated astrophysical or physical situation and make a very simple mathematical model which you could solve to get out the central physics of a situation. And I have never seen anybody who had that ability to that degree. And it made him, I think, in his era, probably the dominant astrophysicist around the world through this particular approach to things. Stephen Hawking began as somebody who did very sophisticated mathematics, but as he gradually lost the use of his hands, and he was a member of my research group when he was losing the use of his hands, he developed a way to do mathematics in his head if the mathematics was geometry and topology. And he developed that ability to a degree that nobody else I have ever seen has. And it was on the basis of then converting physics problems into geometry and topology, and then understanding through manipulating images in his head, understanding how nature behaves, that he made his great discoveries. So 4 very different kinds of minds, very different kinds of approaches. And my thoughts are simply that to realize that there are a number of different ways that you can contribute using whatever techniques work best for you. In fact, it's important to know your own personality. I don't work in quantum gravity, although I think quantum gravity is the most exciting problem of this era. Why? Because I don't want to work in a crowded field. I don't like the idea that if I fail to make a discovery today, somebody else will make it tomorrow or yesterday. I realized early on, I needed lots of elbow room. I needed to work in a field where almost nobody else was working. So for me, the key thing was to find topics that I thought would be very important in the future and help pioneer a new field. And so that's what I did. That's why I chose relativity at the time. It was a time when almost nobody was working in relativity. I chose black holes and gravitational waves. Those are very crowded fields today, but they were not when I started. And I don't work in those fields very much anymore because I don't like to be in a crowded field. That's my personality. On the other hand, many of my collaborators on LIGO, they thrive on interaction with colleagues. They get enormous benefit and enjoyment from working in a collaborative way with large numbers of colleagues. That's the way the LIGO project, by which we detected gravitational waves, works. That's why I'm no longer in LIGO. I don't like operating that way. You should know your own personality and recognize what kind of work you're going to be best at and enjoy the most. Physics is, I think, your generation in Russia has come to understand much better than earlier generations. It's a foundation for moving in many different directions. The kinds of directions that my granddaughter, I urged her to consider before she found something she loved. Teaching, of course, research in universities or institutes such as here at the Prokhorov Institute, not just research in physics. Physics is a foundation for many other areas of science. It can be physics or astronomy, geophysics, biology, engineering. Physics is the foundation for essentially everything except mathematics. And even now, today, theoretical physicists are collaborating with mathematicians on inventing new forms of mathematics in the areas of quantum gravity. The aerospace industry, these are examples of directions in which my own PhD students have gone. All of these directions, the aerospace industry, IT, particularly interesting is business entrepreneur. I have had 2 students who became billionaires by founding and leading biotechnology companies in one case and a worldwide communication company in the other case. They both, after they got their PhDs, they knew what they wanted to do. They then went to business school at Harvard University. And then they became entrepreneurs. And they came back to me, both of them, years later, and said to me, my research, learning physics and working in general relativity was much more useful to me than Harvard Business School. I said, why? He said, because I learned in physics, and it didn't matter what area of physics I worked in, I learned how to take a complicated problem and break it down into a simple form and develop a method to solve the problem. And that technique, which is so central to how we do physics, was key to how you solve a problem in the business world. And much more useful, they said, than what I learned in business school. I had a student who became an analyst for the CIA. Now, you think of the CIA, well, it's like the KGB, they're all spies. No, in order for a government and government leaders to make wise decisions, they need to have people who are able to take information, wherever it comes from, and analyze the information and understand what's really happening based on partial information from many, many different directions. That's what we learn in physics. And that's what you do as an analyst, whether it's for the CIA, for the government in some other area, or in industry. And that is something that a physics preparation is superb for. And these are, as I say, directions in which I've had about more than 50 PhD students, and they went into all of these different areas. I think it's very important to prepare broadly as well as preparing deeply and in narrow areas. So if you're working in a particular narrow, focused area of condensed matter physics, it's really important to also understand what's going on in adjacent areas and outside condensed matter physics in other areas. In my case, I knew I wanted to work in relativity. It was a period before gravitational waves became hot and interesting. But it was a period when I guessed that relativity would become a wonderful area for the future. But I also recognized that the problem with relativity at that time was that there were no experimental data. And if this was going to succeed, the interface with experiment would be crucial. I was going to be a theorist, but being able to talk to experimenters and interact with experimenters, I thought would be very important in the future. So I spent 1 year of 3 years working on my PhD in a laboratory working on experiments. It didn't matter what area of experiment. It happened to be nuclear physics using a cyclotron. And then the other 2 years, I set myself with 1 foot in a theory group led by John Wheeler, another foot in an experimental group led by Robert Dickey. So although my work was theoretical, I understood the experimental side of things closely, and it paid off. It was absolutely essential to my success and my ability to make LIGO a success that I could work very close to experiment, and I had that preparation. I have an impression that the current generation, probably in Russia, certainly in the West, they don't really focus enough on the interface between theory and experiment. Another issue is that you want to look at things broadly because key ideas and tools that are being used in some other area of science can turn out to be central to success in your own field. And I did play a role in taking certain techniques, such as matched asymptotic expansions from applied mathematics or fluid mechanics, bringing them into relativity and using them to understand deep issues like radiation reaction and relativity. Being able to be in an institute where I had contact with people in other fields has been central to the work that I've done. And the third thing is that if you look broadly, you will sometimes see unexpected opportunities. And that was the case with gravitational waves. I didn't plan to work in gravitational waves, but I saw an opportunity there, and I went for it. Later in my career, I didn't plan to work in Hollywood, but I saw an opportunity to start a movie, which became Interstellar, through a collaboration with a friend in Hollywood. I never, ever planned to do that, but I think I've had some impact on non-scientists through inspiring them through science fiction movies. It, as I say, is a result of looking at things broadly. Even within your own field, it's tremendously important to follow what is happening worldwide. Yakov Borisovich Zeldovich, a very close friend of mine, every morning, I think through essentially his entire career, he would get up at about 4 in the morning. In the first several hours of the day, he would read the literature. He would follow what is happening around the world in his own field before he ever went out and talked to anybody else. And that was a big secret of his enormous success in the various fields of physics that he worked in the end in astrophysics, my own field. And I would come here to Moscow, and I would go over to see him in his flat on what then was Vorobyevskaya Shosya, now Ulica Kosigina. And we would sit and we would talk for an hour or two about physics. He always, or astrophysics, he always had some surprising new thing that he had learned through reading the literature that I had missed. And so he was an inspiration for me in that sense. For a career in scientific research, the importance of writing in English can't be overestimated. That's how you influence the work of others around the world. If you're going to influence the work of others, you do it primarily through your written papers and through your written papers in English. And so this was so important to me in training young scientists that the time that I spent mentoring young scientists, I estimate approximately 20% of my time in mentoring went into teaching them how to write good technical English. Every one of my students wound up with their first few papers just covered in red marks that dealt more probably with the English and with how to explain something than with the central science, the ability to explain it being that important. I was reminded recently that back in 1978, I wrote a 5-page treatise for my students on tips on technical writing. I will put that on my website when I get back to California. Just thinking about what I would tell you about, I realized I had that. I went and looked at it and thought, well, some of this is out of date, but some of this is so useful. I'll put it on my website if you want to have some sense of what I was trying to teach my students about writing at that time. So I'm coming nearly to the end. Lecturing, of course, is also important, but if you're a research physicist, it's important, but less important, I think, than the writing, because your impact is largely through your written papers for colleagues. Importance of collegiality. The field in which I worked was a very collegial field, and it was collegial because we all understood the importance of giving credit to other people for their work, even more credit than they deserve. A good example that I feel very strongly about is when I got the telephone call at 2:15 in the morning a year ago from the Nobel Committee saying, it will not surprise you that we are awarding you the Nobel Prize together with Barry Barish and Ray Weiss. I said, it doesn't surprise me at all, but I'm very disappointed. And they were a bit surprised at that. But I was disappointed because it should have gone to the entire team, because the success was a team success. And I think that the general public should be educated about the importance of collaborative work, and that certain kinds of science can only be done by large collaborations. And the Nobel Committee does not do a good job of that. And this is an opportunity that they missed. But it's also an issue that I am very uncomfortable with a Nobel Prize when it's really a prize as a result of the work by many, many other people. And it's so important for me to make that clear to my colleagues how much I appreciate that as part of maintaining collegiality and strong spirit in the field in which I work. Finally, for me, outreach to non-scientists has been terribly important. We have an obligation. I'm sorry. I'm going to shut that off for the moment. We have an obligation to share with the general public the discoveries we make. Because all human beings are born curious, we have the benefit of being able to indulge our curiosity and make discoveries, but we make them in behalf of the entire human race. We have, in a sense, an ethical obligation, I believe, to share what we discover. We also have a financial obligation. LIGO cost $1.1 billion US. They came from the taxpayers of the United States. We owe something back. We owe it to tell them what it is that we have discovered and what the future is of this field. Also, the future of our field rests largely with young people whose parents are not scientists or engineers. And we depend on the general public, on non-scientists, for the lifeblood of the future of our field. And so the outreach to inspire young people who have no background in science, whose parents have no background in science, is tremendously important. My own outreach efforts have been major throughout my life: lectures, articles, books, collaborations today with filmmakers on movies in Hollywood, with a painter on a book that we're working on together about sources of gravitational waves, and even multimedia concerts with musicians. Science interfaced with the art can be a powerful way of inspiring people. And so I have found in this later period of my career this being a really nice and enjoyable way to pursue. So that's all I have, but there are some thoughts for you.